So we're going to do confidence intervals for mean using a t, which is in 6.5. And then we'll also review kind of bootstrap estimation of a standard error and see how they kind of do the same type of thing. So the general scenario is we have a population that we want to study. We want to understand something there. And we're going to take a sample. And in the sample, we're going to make a number of measurements. And the thing that we're targeting up here is a population mean. Greek letter mu. And to estimate that, we're going to calculate x bar, our sample mean. And then we want to make an inferential statement that says, what's our estimate of the population mean, and also how certain are we of that? What's the level of uncertainty that's represented by an interval? So our inference going up, we're going to do kind of a lower value to an upper value. That gives us a confidence interval that describes where we think the population is. And in the if all the xi's have mean mu and a standard deviation sigma, and they're independent of one another, there's a few things that we know from probability theory, from dealing with the probabilities of random variables, that we know about x bar. Right? That the expected value of x bar is mu, so on average, our sample is giving us the right value. Some samples will be higher, some will be lower, but on average, they should give us the right thing. The standard deviation of x bar, if all the x's have the same standard deviation and they're dependent of one another, that's really where independence comes in, is sigma over the square root of n. So our accuracy for x bar can be a lot more accurate than an individual observation based on big samples. And central limit theorem, x bar is approximately normal. Normally distributed. So if we calculate probabilities related to x bar with a normal curve, bell-shaped curve, z-score, let's calculate that, the probability should be pretty accurate. Even if the distribution of the x's themselves is highly non-normal, right? Even if it's Poisson counts that are extremely skewed, or something that is all bunched up, near 100 and then trailing off, and just completely non-normal. If you get a large enough sample, in large. It can happen with very moderate n, as long as the original distribution is not too skewed. But the more extreme the distribution underlying things is, the larger n you really need. Most books say 30, 40, something like that. But it might be really a lot more than that if it's highly skewed, or you might be able to get by with less. But in any case, it's approximately normal. So we use this normal theory to produce a confidence interval for mu. Ci for mu that had the form x bar minus some normal value times the standard error up to x bar, plus some normal value times standard error. And our formula for standard error was the standard deviation of x bar, sigma over the square root of n, x bar plus z times sigma over the square root of n. And that z value is a value from the normal that determined by the confidence level. So for instance, if we have this picture of a standard normal bell-shaped curve, standard normal centered at 0 there. We want 95% confidence. We found the z-value that gave 95% of our results. We standardize things about 95% of the values. That would be here z, right, and negative z under that table. Right? So if we have 95%, what's left in these tail areas? 5% in each one, or total 5%, and 2.5, 0.025 here. And so the z-value we're looking at is not the 95th percentile, but this 97.5th percentile. And under our normal curve, that is to be 1.96. So for a 95% confidence interval, our interval is going to be like that above there with the 1.96 put in. Yep. So we're going to have x bar, I'll write it as plus or minus 1.96. Let's see what we're squared with. And so that should work pretty well. The one limitation of this is usually we don't know sigma. We don't really have, we're trying to estimate the mean, so the chances that we would know a very accurate value for sigma is pretty low. So today we're going to deal with that, or we're going to replace that sigma value by just the sample standard deviation. The value of S that we would calculate from a set of values, just like at the beginning of the course with the descriptive statistics. So sigma is unknown. All right, so we're going to get our data x1, x2, xn, and we're going to calculate x bar, and we're also going to calculate s. S was the symbol is xi minus x bar squared divided by a minus 1, and the square root here. My sample standard deviation. And so in our interval, we're going to have our x bar, minus something here, and then s over the square root of n, up to x bar plus something here, and s over the square root of n. So instead of sigma over square root of n, we're going to have an s over the square root of n. And to compensate for the fact that we're replacing something known by something random, right, we're going to put in it's a t distribution. T value instead of normal. So t value is from a t distribution. What is this t distribution? It's like a normal. Right? It's bell-shaped. It's centered at 0. There's a little bit more variables. There's a little bit more area in the tails. So our t values are going to be a little bit bigger. Right? Instead of 1.96, it's going to be 2.02 or something like that. We're compensating for the fact that instead of knowing sigma, we're estimating. So if we want to preserve 95% coverage, right, 95% of our intervals make it, right, we have to do something because some of those intervals will be too short, because S will be small in our sample. Every once in a while, S will be too big in our sample. It'll be larger than sigma. But particularly when it's smaller, our intervals get shorter. And if we keep using 1.96 of a normal, more of them are going to miss, because we're going to get some small values of the standard deviation. So it compensates for that. So the t distribution is basically the same picture. There's a different t distribution for every sample size. T of 1, T of 2, T of 3, T of 99, T of 9,000, whatever. This n minus 1 is referred to the degrees of freedom as dm. And it's n minus 1, one less than the sample size. This is standard terminology for the index that's on the t distribution. It comes really from things in linear algebra about how many restrictions there are on n data points. If there's an average, there's one restriction. So that's where we get n minus 1 in this case. And so we're going to find a point, say for 95% confidence, that has 95% in here. So again, there's 2.5% here and 2.5% above. And the thing that's copied there on the front, is everybody have a copy of the? Yep. Right, is a t table. So it gives the percentage points of a t distribution. And on the left column are the degrees of freedom, like 1, 2, 3, and so on. Down to 120, or that is infinity at the bottom. And then it gives percentiles, 75, 80, 85, and so on. Right, so for 95%, we have to look up the 0.975 column of this thing. Right? And so after a little while, above 11 or so, above 16, 21, this number is a little bit above 2. Right? The normal value is 1.96, and this is a little bit bigger to compensate for the uncertainty. So let's use this in an example. Right? So just an example. This is an example from life science statistics. Monarch butterfly wing. Butterfly wing. The area of their wings is measured in centimeters squared. And suppose you collect 14 butterflies, and the average wing area is 32.81 centimeters squared, with a standard deviation of 2.48 centimeters squared. What's a 95% confidence for the average wing area? Of similar monarch butterflies. You might be interested in this. If you have a sample from monarchs from one particular site, you might want to compare that to a general population. Maybe you had a sample from that site 10 years ago. And are they changing because of global warming or other factors? Are they becoming bigger or smaller? How is the species kind of dynamic shifting? Well, we're going to need a t-value. We need a t-value that has 13 degrees of freedom and is 0.975 percentile for 95%. So looking at this table, go to the row, 4 degrees of freedom at 13, and go over to 0.975, and what do you see there? Yes?
2.160.
Yeah. 2.160. Right? So we're going to get x bar plus or minus the t-value times standard error, or x bar plus or minus our t-value s over the square root of n. Right, with the formula, it's always important to distinguish s versus s over the square root of n. Right? So we get 32.81 plus or minus our 2.16. And now s was 2.48, and square root of 14. So we get an interval of 31.4 up to 34.2 centimeters squared. Right, yeah.
So if it's a 95% confidence interval, why are we using 0.975?
So for the 99%, 95% confidence interval, right, we gotta get the point that has 95% between 2 points. So if it's 95% between 2 points, this table is going to look up below a point. So it includes one of those tail areas. Right? So in this type of picture, right, if we want 95%, if this is t, this is negative t, we want 95% in this area. The point that we can look up on our table includes also this little piece over here. So if it's 95%, half of it is 0.025, and add those together to 0.975, 0.95 plus that little tail area, right? And so you look up the 0.97, so it's 0.16. So when n is 14, or degrees of freedom is 13. What about a 90% interval? How is that going to change? What t-value do we look up to use for this one? Yeah.
0.95 because one of the tails is 5%.
We use 0.95, so you get this picture of 90% in the middle, between zeros in the middle, t, negative t. That's going to leave 5% over here, and 5% over here. Right, so our table is going to have, look up the 0.95 value. What is that value in this case? Yeah. Right. A little bit less. Right. If we only want to cover 90% of the time, we don't need to go quite as far out. To cover 95% of the time, we got to go out and get more area. So it's x bar plus or minus our t-value times the standard error. 32.81 plus or minus now our t-value 1.771. Our standard error was 2.48 over the square root of 14. And that comes out to be 31.6 to 34.0 square centimeters. A little narrower, but we're a little bit less confident that it actually covers. Any questions? Kind of it's not that complex of a shift, but a new table to do. You have to realize at the beginning of the data, standard deviation from the data values from these points. So let's look at a new example. So looking at Blue Jay build lengths. This is measured in millimeters. Let's say you collect just 5 of these individuals, and this one and the average. Sometimes books use y, so we'll use y in this example for 0.9, and the standard deviation 0.085. We're only taking 5 individuals, right? So we want to do 95% confidence interval. Let's go back to 95 for average build length. You want to write down the formula, look up your
Wouldn't that be X bar instead of Y bar?
It could be called either thing. So, I've been calling it X bar. Some books would say your measurements are Y1, Y2, YN, and then you calculate Y bar, standard deviation of the Y values. Whatever symbols used there, you have 5 observations. It's the average standard deviation. When I write questions, I mostly say this is the sample average, sample standard deviation, rather than give it a symbol. So you can use, as you read other books or other sources, it might change the letter on you. Okay. But if you do that one, you think, well, what if you got the same statistic, the same y bar and standard deviation, but you had 20 as a sample size. How is that going to change your interval? So what did you write down? Work it. What did you produce for the confidence? What did you write? What did you write down? What formula do you want?
So I think it would be 25 plus 9, 25.419 plus or minus 2.776 times 0.0085 over the square root of 5.
I think it's 0.085, so I don't know if
I think did I have an extra zero?
you had an extra 0 in there. So I put 0 point, but in any case, that, except for that one number thing, is right? So this is the average, plus or minus the t-value, and then s over the square root of n. Yep. Right. And so that t, how did you get the t-value? Right, that 2.776. Just 5. So which row do you look up? 4, right? The degrees of freedom in this case is n minus 1 over 4. The 0.975 column. So our p-value is 2.776. Quite a bit bigger than 1.96. We only have 5 observations. You know, you get 5 observations kind of close together, and that value of s is really small. Right? But you still want a lot of those intervals to cover, so you use a bigger multiplier. That's the compensation. So numerically, you can use R kind of as a calculator. There's a command in R called Qt. It does the quantiles of a t distribution. So you can put in whatever percentile you want. So 0.975 in here are the degrees of freedom, and it gave 2.776445. And we only need to use really about the first few decimal places is fine. So adding that onto there, the upper interval 25.52, lower interval 25.31, and that would be the 95% confidence interval for the average building. If you change it, n equal 20, is the interval going to be wider or narrower? Narrower, right? It could be narrower again. So how is it going to be narrower? What part of the formula is going to change? Yep.
The square root.
Yeah, the most direct thing is the square root, right? That becomes square root of 20 instead of square root of 5. What's the other change? T, yeah, degrees of freedom. We don't have to, we're not stuck with this huge t value anymore. So x bar plus or minus t s over the square root of n. And our same number here, 25.419 plus or minus, it's 0.085. Now square root of 20. So that's the change. We're looking at the T table, to Rosner's T table here, his version of it, under the 975 column. Now we look at that T. So 2.093. 2.0993. And so this is smaller, and this divided by the square root makes it smaller, and our intervals is going to be smaller. It's still 95% interval, right? 95% of intervals for this sample size made this way, cover. Right? That's still the property. It's still 95%, even though it's narrower. It does not become a better percentage just because we have a bigger sample size. Right? 95% is the areas we cut off, and so that's just a property we've decided we like. That's accepted practice, so that we use that. On the handout, on the back of the page, is kind of an illustration of the impact of sample size. So in this particular example, say the population really had an average of 25.4 and a standard deviation of 0.8. And then you take a sample of size 5. Well, one time you get this average that we've dealt with here, and the standard deviation, and this would be our confidence interval. You take another 5 birds, you might end up with this average is in the standard deviation and get this interval. Or a different 5 birds, you're going to get these different intervals. And both the average and the standard deviation will change. Both of these use the t distribution with 4 degrees of freedom to get that cutoff, that multiplier value. And many of them cover, this one looks like it misses, but that's the interval. We switch to 20, same population, so now pick samples of size 20. The intervals are a lot smaller because we get square root of 20, and we get a t value is not quite as big, and so the intervals are actually less than half as wide, because 4 times the sample size makes it, the square root of n business makes it half as big. The t also gets smaller, so these are tighter. Some of those intervals make it, and some of them don't. But any questions? Yes?
Will you specific, will you tell us which one to use, or is it just like?
So the default really is primarily to use a t distribution, and so the phrasing I would do is say that this is the mean and standard deviation based on those 5 birds or 20 birds. So it's based on those, so it's the sample values of x bar and sample value of standard deviation. If in some of these other problems where you use sigma and the normal, right, it says that the standard deviation of the population is this. Right, it tells you this is this has a measurement error or variability that's this value. Now we have a sample of size 5, and their average is this. So it kind of separates the average, the population value versus what's in the sample. Before the exam, we'll look at some wording of some questions. And the thing that's done in practice really is this T procedure. Okay. New example. So say you're interested in measuring bone mineral density. And you have a sample of 94 women, ages 45 to 64, and so the average bone mineral density is reported as 0.878 grams per square centimeter. I wonder if it's cubic, but I'm just keep it what my notes says. And the standard deviation of the measurement is 0.126 grams per centimeter squared. There's some procedure for measuring bone mineral density. Do a scan, weight of limbs relative to their size, like that. The density. And we could do a 95% confidence interval for the average of density in similar women. Now, one thing we might ask also, what's the standard error? Kind of separately from the confidence, what's the standard error for X bar? And that's just a calculation of S over the square root. 0.126 over the square root of 94. And that's 0.013. That's also in grams per centimeter squared. For 95% confidence interval, we're going to need a t-value, right? Can we get this t-value from the table? What degrees of freedom should we use? N minus 1. 93. There's 93 in our table. No. Right? There is a t-value. There is a distribution with every degrees of freedom. You can actually do generalizations of this to do every decimal, right? But you could do 90. It exists. It's just not listed on our table. I mean, you get quite a few pages if you want to list them. Hundreds of them. Right? But what do we have? We have 60 and 120 are there. Right, what's the t-value for 95% for 60? .975. There's always that business. We want 95%. That's 95 central percent. Yeah.
It's 2.002.
2.00. And then 120. Right, just below that, 1.98. Right. Does anybody have any questions about these numbers? I guess I have it here. Bring up the table. Right? So we're looking in this 0.975 column, right? And then down here at 60 and 120, we don't have 93, 94, 93. Right. But at 60, it's 2, and at 120, it's 1.9. So what value do you want to use for 93? Like 1.99. Well, you could go down to 60. You could be conservative and say, well, let's pretend we don't have more sample size. We could go down to 2. That'd be fine. But I'm also comfortable saying, well, let's try 1.99. That's approximately. In a real scientific application or business or things that you're doing, you probably use a computer to get the decimal exactly. So it's about 1.99. But you're right. If you wanted to be conservative, you could go down to 2 because you could choose a smaller one, and that makes your interval just a little bit wider, so you have just a little bit more than 95% coverage, and that's okay. So you can either use this one, or 1.99 seems reasonable as a compromise in there. So our interval then given everything. So x bar plus or minus a t-value times the standard error. I'll use this in here. 0.878 plus or minus 1.99. And our standard error 0.013 over there. As an interval, that goes 0.852 to 0.904 grams per centimeter squared. So yeah, that'd be 95% confidence interval for bone density. Now, if this was a group that was receiving some type of treatment, some type of supplement, estrogen supplement, calcium supplement, something like that, or maybe an exercise program, because your bones will get stronger the more you exercise. Tension helps, in any case, there are different things that could be done. So it could be a treatment group versus that. Yeah.
If it's binomial, do you use like the probability instead of the mean?
Yeah. So we'll return to that. So confidence intervals so in a binomial setting, we're often interested in what is p, what is that proportion, right? So in a binomial, we'll observe, the number, the sample proportion. Yeah. So we will use kind of a sample proportion plus or minus. Now it's an issue in probability theory that the normal approximation to binomial is a little bit different. So we still use normal there. We still use the normal in that. We'll try to just keep that straight. The variability, the standard error for p hat, is p times 1 minus p over n, which is square root of all that. And so that's the standard error we want to put there. But we don't know p, so we plug in p hat, right? So it'll be p hat plus or minus a normal value, and then p hat 1 minus p hat over n. But I was planning to do a few more examples with that, on Wednesday. But yeah, so instead of the means, it's proportions. Right? And it follows the same thing. Estimate plus or minus a distribution value, right, times standard error. Kind of there's that parallel structure when we're dealing with different problems. And one thing we go through going into the second exam is how do you tell which formula to use? What are the key words that'll be in there that indicate, oh, it's about a proportion? Usually binomials are talking about proportions, or the number of people out of a certain number, whereas these things that are, flow and mineral density or something are talking about averages and giving you a standard deviation as well, sample size. So there's a little bit different phrasing of the problems for the different parts. So if it's not on the table, right, you can take the smaller value just below where to kind of interpolate for those. So we talked last time that sometimes there's a simulation way of getting at standard error. Bootstrap, where you'd have our data, and if we could get more samples of data, our standard error really is the standard deviation of x bars. If we had a whole bunch of x bars, the standard error that we would want would be that. Now, we have the formula that if the standard deviation of x is sigma, then the standard deviation of average of a bunch is sigma over square root of n. And so now we use s as the square root of n as an estimate of that standard error. And the key, the bootstrap was another way of kind of simulating and getting to that standard error. So let's review that, and then we'll do one thing on computing. We're still going to do x bar plus or minus a t value times standard error, but instead of using s over square root of n, we're now looking at bootstrap version of standard error to get a different way of estimating it. And there's a formula, and it works just perfectly fine. It will probably be a very standard thing to do. As you get into more complicated problems, the bootstrap has additional benefit. It can be done in situations where just a one simple formula like s over square root of n doesn't quite work. I've encountered this in a number of research projects where the data come in, there's some missing values or values that need to be edited, and some are kind of unreasonably high or transformed to be more reasonable. And then there's a subsetting then, and they get weights applied to them. And then you do a weighted average. And so it's a little bit more complex. And so one alternative is do more mathematics to find the actual variance formula, which is tricky, or an approximation to it, or do a bootstrap. So the bootstrap is quicker to program and pretty much accepted for many applications now. So the bootstrap idea is we have our population, and we have mu. And we're going to take one sample and get our data x1, x2, xn, and we're going to compute x bar. But we wonder, what is the standard error up here to use in this formula, x bar plus or minus t times the standard error. And the bootstrap takes these data and then generates a large number of capital B bootstrap samples. Each bootstrap sample is going to generate x1 star, x2 star, x and n star for each observation. Each xi star is sampled from our x1, x2, xn with replacement, that you could repeat values, you can leave some values out, you can get some slight differences there. And each of these bootstrap samples, we're going to calculate an average. Let's put a little b here for index. And then our standard error estimate from bootstrap is the standard deviation of these x bars, different x bars, from these different bootstrap samples. Okay. As if you could do repeated sampling and get a bunch of x bars and look at their actual standard deviations. We do this little bootstrap modification to try and get at that. So it becomes a simulation-based way of getting at the standard deviations. So let's look. Some computer code is given on the second page of the handout. And we'll kind of step through that as an example. Right? And so this level of programming for things is a little bit more than you need to do for this course. It kind of showed you a couple of extra little techniques to do. These might be useful if you are using some data in a project at some point or wanted to simulate something. But it would just be kind of an example. One famous data set is in the statistics literature is this IRIS data set, HELP IRIS. It's an IRIS data set by Edgar Anderson. It was also used by Ronald Fisher, who was in some sense at the beginning of mathematical statistics when he was writing in the late 1800s, 1910s, 1920s, about some of the underlying theories and ideas that underlie experimental design and statistical analysis. And so this one, there's 150 different flowers, 3 different species of irises. And so here's Iris setosa, nice little plant here, right? Here's Virginica, that's another one in this group. Right? So anyway, there's 3, and so they have sepal lengths and sepal widths, and petal lengths and petal widths. So there's 4 different measurements that are taken of these plants. So for instance, Iris, the first 3 rows of the data set give measurements there of sepal length, width, petal length and width, and species. There are 3 different species. I didn't attach it. Did I attach that? Try it. Okay. Now it'll work for me. So I had to attach the data set so it knows to look for those variable names separately. So it has 3 different things. There's 50 of each type. One thing that this data set is used for is as an example of ways to make up statistical functions for discriminating or classifying different species, right, based on their measurements. So if you do a plot of petal width versus petal width, for instance, you see different, there's the petal length and petal width in this scatter plot. They're pretty strongly associated with one another. But there's one group that's kind of small and another couple groups actually that are up here. And so this kind of the relationship between these things kind of separates out one of the species as being smaller than the others. This is a typo there. Petal length and sepal width. See, here's another kind of separation between these. And so this is a situation that's sometimes used in courses that are called courses on multivariate data analysis. We use all 4 variables at once to build one rule for classifying it. And so different algorithms can be used to try and separate this out. That if you could project these measurements in 3-dimensional or 4-dimensional space, you actually see kind of a separation of the 3 species. We quite can't see it here. R has this command called pairs. So the columns 1 through 4 are my continuous ones. If you do this, it will make a nice plot that shows you all 4 variables at once, right? So in this plot, this might be a little hard to read details from the back. Petal width is a variable. It's on this axis and this axis and this axis here. Down here, it's on the vertical one. So this is a plot of petal width versus petal length. And this one is petal width versus sepal length. So you see all the different pairs together. And in a class like regression analysis, where you're looking at what predicts another one, you would pick out on some of these things, and you see some of the different separations that are there. It's always good to kind of look at the data. Right? So if we wanted to do just a confidence interval for, say, one of these variables, say sepal length, right? We could look at the mean of sepal length. But let's do it within one species. Right? In R, you can refer to a subset by giving it, so Setosa is one species. So the average length of species, not series. There we go. The average sepal length, let's do a histogram of that thing. Sepal length. And sepal length by species. The Setosa one. Let's see what the data. All right, this is the sepal length for the Setosa ones. And so the sample average, right, let's put a vertical line at this thing, at the mean. That group. I'll just type 5, 6, and make it red. Red. Not sure if it's going to work. Okay. Let's see now. Color is red. There we go. So there, the average is actually falls back right on that line there. And there's a split of the histogram there. It's almost invisible, but not quite. So that would be the average at 5.06. The standard deviation of those things is about 0.35. So the individuals, 0.35, about 2 standard deviations is about 0.7. So if you go up about 0.7, 5.7, you're up here. If you go down 0.7, you're kind of down here. So that standard deviation describes the individual flower measurements, right? A standard error for the average, right? You got to take square root. There's 50 of that species. It's about 0.05, 0.0498. Right? So it's a lot smaller based on that. The t-value, we need the 0.975 cutoff for that. There's a t distribution, and again, this qt. You put the percentile you want in there, like the 0.975, and the degrees of freedom in there. And so we had 50 observations, so that value is just about a little over 2. If we want to do a confidence interval for the average sepal length in this species, right, it's going to be the mean. Minus this t-value, qt, times the standard error. So this whole formula is going to get a little bit long and kind of scroll off the. So I can press return, and then it lets me continue on the next line. So that's the lower part. Adding it gives me the upper one. So we get a confidence interval that's about 0.491 with rounding, up to about 5.11 as a confidence interval. So that would be one measurement on one species. But any questions about it? So as you're doing your homework, if you want to check any answers based on R, you can kind of program it to do some of those. You're welcome to do that. Within R, there's a command called split, where you can split one variable into different groups based on the other levels of another one. So if we want to split all the sepal lengths by species and create 3 different groups, we can do that. That will split them out. So split by itself as a command. This make it big. Right. Creates 3 different list objects. Split it by those. Then there's a command called sapply. It's like applying something, but to the split variables. It's split up into that list. And it says take the mean or average for each one. So we can get the average for the 3 different groups, right, all at once. If you change the variable name here, you can get the averages for the sepal width and petal width and other things like that. The other thing you can do is you can change the function over here. So instead of doing the mean, you can do the standard deviation. So we can do standard deviations of all those. In fact, instead of, we can save these things. Right? So x bar. Now x bar is the averages. We can save S. Let me go back up. These are the standard deviations. Right? The standard errors should be, well, S is 50 for every one, so we'll just do that. So now we have 3 different standard errors. We have 3 different x bars. So the confidence interval for all 3 species, all of, simultaneously, is x bar, minus this QT value, 975. They each had 50, so degrees for 49 for each, times standard error. Those are the 3 lower ones, and then the 3 upper ones. So one interval goes 4.9 to 5.1 for Setosa. Versicolor goes 4.79 up to 6.08, and Virginica is 6.4 over to 6.8. Do these 3 species look like they have similar averages? Or just pretty, if this is a kind of a random sample from the species representative somehow, is it pretty clear that the averages are really quite different? Setosa is down here around 5. This one's up here about 4.85 or 4.9 or something. And this one's way over 6. And the intervals don't overlap. So those populations, likely, the true values really are separated. And even though if you do a box plot of petal, this was sepal length as a function of species, it will produce 3 different box plots. So the medians are quite different. But there are some Setosas that are longer than some Virginicas, and there's versicolors, and there's one Virginica that is particularly small, and there's more variability in some of these. So the individual values do overlap. It's not like they're 100% separated, and you would just automatically see one and say, oh, that's small, medium, and large, and I know the 3 species. Based on size alone, it doesn't quite do it. But the averages are more precisely determined, and it's clear that they are not the same. Right. Getting at standard errors with Bootstrap, right? How would you code something like that? So when we looked at it before, we just did 1 variable at a time. Now we're going to do 4 variables at a time. So setting a random number seed sets up the random number generator. So if we all start at the same spot, we'll all get the same results. Right? I'm going to do 1,000 simulations, 1,000 XBAR Bootstrap samples. I'm going to set up some place to store it. And I'm going to set up a matrix that has capital B rows, so 1,000 rows. But I'm going to store 4 different variables. So I'm going to do 4 columns. And I'm going to name those columns sepal length, sepal width, just kind of abbreviations there. Then I'm going to do my little loop, right, 1,000 times. And the numbers, the first 50 are all Setosa. So the data set's organized that way, one species to the next. And so instead of picking the numbers, right, so the sepal length, the first 50 values here, these are the values. So instead of picking from these, I'm going to pick from the row numbers 1 through 50. Right? If I pick 1 through 50, I can translate that into these different variables. If I pick the third person, the third one, the value is 4.7. I pick the third, and then I pick the 17th, I get 5.4, so I can translate. I can either sample values, or I can sample row numbers that indicate which unit I'm supposed to get. So this thing here samples from the numbers 1 through 50, 50 times. A replacement T or true, it reads it the same way. So S is going to indicate which rows are in my Bootstrap sample. And then I'm going to take my sepal lengths and take those. There might be some duplicates. in there, and with the mean, and I'm going to say the first column, the first place I'm going to save it, for iteration B is going to be that average. And then I'm going to say the widths in the second place, the lengths in the third column, the petal widths in the fourth column. And then it goes back and takes a new sample and moves on to B equals 2 and fills up. So this business here, right, if I do that, right, it runs and it's done. So the standard deviation of this should be like standard error. So the standard deviation of this first one here is the first column was SL, so sepal length. And so this would be the standard deviation there. And I got the same number that I had before because I used the same random number code. Right? If you looked at, so you could do a confidence interval, right? You could take the average minus the t-value times the standard error, right? And you get this as a confidence interval. Now, if you take the standard deviation of the sepal lengths themselves, all 50 observations, that's S. And S over square root of it, you have to have that there. So if you do it by the formula, instead of the bootstrap, you get just about the same number. So 4.9081, 5.1039 is the interval. If you did it based on the formula, you would get something that is off in, third or fourth decimal place, quite similar. So we can do these things with simulation, and the bootstrap kind of mimics that. So where are we in terms of big ideas? We had the population and some value of mu that we want to know, and we take a sample, we get data, x1, x2, xn, and based on this, we're going to calculate x bar and s based on the level of confidence that we want, usually 95%, but just to emphasize understanding their tables and things, we might change it a little bit. And n minus 1 is degrees of freedom. This thing gives us a t-value. And so our confidence interval for mu. We always do confidence interval for the population sample. Population that's not known. That's where we're doing inputs. We never do a confidence interval for x bar. Once you get your data, you know x bar. So x bar plus or minus t value times standard error. X bar plus or minus t s over the square root of n. And that should give you an interval that you can act confidently, go forward, do planning, do decision making, as if it's probably correct. We'll come back on Wednesday and do a variation on proportions and maybe something else. See if we make other. It's good to look at that to see if you can find that, because on the exams I can give you a copy of that table. So you can do it in either one, but I would strongly suggest that you could figure out, can you get it off the table?
And why do we use the 97.5 column instead of the
95? Because we want 95% in the middle,
Yeah.
right? And so there's 95% in the middle plus one tail. There's that one little extra part in there, off to the side.
Okay.
So if it's 95% in the middle, there's 2.5% on this side and 2.5% on this one.
Okay.
And the way our table's set up, it does the interval up to a point.
Okay.
So you gotta-
So we want to include the tail?
Yeah.
Oh, why?
Well, we're going to take the tail as a value between plus or minus that.
Yeah.
So when we report the interval, we kind of cut off both halves.
Okay.
But to find the pace that will have 95% in the middle, another way of thinking about it is if you want 95% in the middle, there's only 2.5% up above.
That's true.
Yeah, so you got to go all the way up to this point to get that. And if you flip it around, you still are cutting off this other
Oh.
tail. When you make the
okay.
interval, it cuts off.
Okay. Okay, thank you.
Sure.
I've been so confused, I'm just like, what's going on?
Yeah, look back at that, because that's also how we got the normal. We did the same, the 95% was really the 97.5 percentile for that one.
Okay, thank you.
Sure.